in most cases. And then the runtime is mostly comparable. This is now much more subjective because it depends how much we optimized our PRM. This is just on a CPU. It's not on, it's not a GPU or FPGA or anything like this. Okay, but we have comparable, competitive, I think, runtimes, and those are going to get better. I actually really like this one, right? So there's one case where the solve time was almost 0. And the reason for that is actually a clever preprocessing algorithm that Tabia came up with, that basically just looking at the discrete graph, if you can prove that you don't need to visit a bunch of cells, you can trim the graph before you start. And so in a good way, you actually find when there's just a short path to the goal and that's all you need to do to explore, then it makes the simple instances fast. Yeah, so it works for lots of different robotics sort of applications. This is the bimanual one again, just to show how tight that is and it's solving. So we did not compare this one to PRM. PRM, I think, it's hard to get to work in 14 degrees of freedom, right? Takes many, many samples. Most people will, when they have a bimanual mobile manipulator, for instance, they will kind of plan with one arm or plan with the other arm, but you can hold the other one fixed. So this is something that I think is a good application for graph of convex sets, is we can plan in a few seconds, even on the bimanual cases. Okay, so I talked about the motion planning instance, okay, but it's actually a more general framework, right? Tobias looked at a bunch of different mixed combinatorial continuous optimization problems. Oftentimes, not in every instance, but there's a number of problems where this is a kind of a nice way to write the problem down, and you get tighter convex relaxations. I think for task and motion planning, there's a natural, again, relationship between the discrete decisions and the logical conditions and the continuous optimization that I think we're not exploiting that connection in a deep way yet, and we can. This is version 0.1, I would say, of a framework, right? So I think, I hope you all get excited about it, help it grow, but it's competing with tools that have been optimized for a long time, and this is just the first version. I would say, compared to the RRT, for instance, it's hard to implement. It's not, it's not a few lines of code. It's built on a tool chain which has made the mathematical abstractions of perspective functions and everything good. It's clean, but it's harder to implement, harder to type in yourself. Totally possible, but just a little bit more sophisticated. So I think in order to make it useful to everybody, we've tried to provide a mature implementation, and hopefully you'll check it out. There's a lot more we're currently doing and that we want to do. For instance, just generalizing, we start to talk to people who are actually would consider using this, and they say, okay, well, we want end effector constraints on velocity, and we don't want to spill the salad when we're moving, and there's just other constraints that you want to put in. Dynamics are a particular case we're working very hard on, but I just left that out of this first presentation. But also, I think there's a lot of reasons to be optimistic about the solve times. The work we showed right now is just handing it to a standard custom solver. But this problem is sort of dripping with gobs of structure that you could, that we don't know how, in the current way that you talk to a convex optimization program, we can't, in the interface of like A and B matrices, we can't tell it about all the structure we know from the graph. So I think there's a lot of room for that, and we're starting to work on custom solvers. Or you can warm start it, for instance, if you're really executing very similar trajectories lots of times, I think you could just have that small runtime almost all the time. So we put that mature implementation in Drake, and I have to just tell you for a second about what's going on in Drake. So Drake is a couple things. It does have a good simulation engine, a physics engine, compared to for manipulation. I think it's got a very rich contact modeling library, an approach to contact modeling that is, I think, better for simulation and for optimization than a lot of the standard approaches. In particular, where most people who are simulating contact, including us for many, many years, you'd always summarize the forces between two bodies with point forces. And this is just a fundamentally bad operation. And we're doing more work these days inside Drake to do, just take the extra work of thinking about the entire penetration of two bodies, finding a surface integral and just taking, the force calculation integrated over that entire surface. This makes a huge difference in terms of smoothness of the simulation landscape and optimization landscape. Okay, so for manipulation and for sim to real manipulation, I think it's state of the art. And inside there's lots of, this is now where we put our mature code. So if inside Drake, there's an optimization hierarchy, you can interface with your favorite optimization engines through this, and you can you can call it the graph of convex sets and just build up your graph saying, here's a node, here's a node, here's a node, here's an edge, here's my costs on that edge and constraints, and boom, go. It'll solve, if you have Gurobi on your system, it'll solve that. If you have MOSEC on your system, it sort of does all that work for you. And I hope that will reduce the barrier of giving this a try and extending it. Okay, so I wanted to tell you, about one real thing here, which is this new strong mixed integer convex formulation for shortest path problems over convex regions. It reduces to shortest path as regions become points. That's, I think, a key thing that we haven't broke it. The problem class is still NP hard. We haven't changed that. But we have either efficient branch and bound, or we have convex relaxations that are often tight. In particular, they're tight enough that with a little bit of rounding, we almost always get the optimal solution. I showed you this initial application in the manipulator planning at the dynamic limits. Okay, and I hope you'll give it a shot. So did we accomplish the deeper connections between these? This is, of course, just the beginning. But I do think that some of the combinatorial optimization, which looks so similar to the problems we were writing down in trajectory optimization, this is maybe just one of the obvious sort of connections that was waiting there for us to just write better. And I think that helps. I think it opens up what trajectory optimization, what we should expect out of our trajectory optimization. If you want more, the demo I ran was actually right in the course notes for my class. Nowadays, I rarely write an example if it's not in the course notes these days. So there's online class and lecture notes and everything inside that. And I'll stop by leaving the paper references up, and I wanted to leave some time for questions.
Great, we have a number of minutes for questions, so.
So I'll admit this is probably far too elementary a question for this presentation, but so you have this system of relaxation where you go from essentially Boolean variables to variables that are continuous between 0 and 1. And it seems to me like you've essentially gone from each of those variables having exactly 2 options to having uncountably infinitely many options. How is that easier?
Okay. I mean, it's about the convexity of the set. So if I have, if in the simple case of think about having a linear objective, okay, which says I want to be in some, I could go to the whiteboard, but I think it's really about having a continuous family, but it's a good continuous family where everything's connected and right. It's a convex set, and you have an objective which is pointing you in one direction. And so by the objective pushing you into some corner of that, let's say, of that bounding box, if there's multiples, it does make the problem easier, right? You can use standard algorithms, simplex algorithms to walk the corners or things like this. It actually does break some of that complexity.
Oh, so if you have something like n Booleans, you can then model that as an n-dimensional hypercube.
That's right.
From 0 to 1, and then you can use something like any optimization algorithm like the ones you discussed.
I think that's exactly right. So think about the n-dimensional hypercube. Instead of having to visit every corner, I can think about the box and I can point myself in some direction and just find the closest. Yeah, that's a great.
Thank you very much. Excellent talk. 2 questions from my perspective. I'm a little older than the average audience. visiting through convex sets. It's called the TSP with neighborhoods. And Mitchell worked on it for 10, 15 years with almost tight bounds. So it's my question number one, what's the connection of your work with all the great algorithms to do TSP with neighborhoods with tight bounds? Second question, I might confuse you because it's completely unrelated. So my apologies. In optimal control, we have the notion of local optimality. If you found the globally optimal path, it is also optimal between any two via points. It seems much more powerful and natural approach than what you are trying to do. You are doing something strange. You are crossing obstacles. Wouldn't you prefer to start from the start using the notion of local optimality? I think it's also called dynamic programming or something, and get much more effective algorithms. I'm a little puzzled. So thank you.
Well, let me go back with you. So sorry. Local optimality is simple. We get that from the nonlinear trajectory optimization. But it's insufficient. Like locally optimal solutions are often far worse than the globally optimal solution.
But you search locally.
What's that?
You search locally, pieces by piece. I think it's called dynamic programming, I think.
We know dynamic programming. It depends how you parameterize your dynamic programming algorithm, right? A lot of them do not scale. I mean, sort of a nice dynamic programming algorithm on a mesh or something like this will tend to work very well up to maybe 5 or 6 dimensions if you're willing to compute. But we're trying to scale to much higher dimensions than that.
Gotcha.
And on the first one, so there are, I think, in fact, if you know any references that we might have missed, we did look carefully at all the TSP kind of algorithms, and I think they are not quite as general as this. There are places where those instances are very similar, and we try to compare. Okay. But I would actually, we should talk with you afterwards just to see if there's anything we've missed.
Okay.
Yeah.
Okay, thanks, Russ. It was a wonderful talk. I appreciate it. Especially like the interleaving of coding in the middle there. That was good. So it looked like at one point you were essentially building a volumetric representation or under approximation of the free part of the configuration space. I thought that was kind of hard to do. So how are you getting away with that? Is it because the particular models that you're using are somewhat simple in terms of geometric primitives, or what's going on there? I just kind of remember that as being difficult, but I've been away for a while. Maybe it got easy in the last decade or so.
So no, I think that's a fair question. So the question, I would say that what a PRM or an RRT is doing is also making a sample-based approximation of that free space, right? So anything you can do for PRM, I would say, let's just, every time I make a sample, spend extra time to come up with a local region. And we'd have the same sort of guarantees. It would probabilistically, we'd draw some sample that's outside of all of our regions, we would add a set, and we would expect, in the same sort of probabilistic completeness kind of sense, we would eventually cover the space. We're not saying something stronger than that.
If you claim a volume, are you guaranteed that that's collision free, or are you not worried about that?
We have 2 versions. We have one that's very fast, that doesn't make the guarantee. And we have a second version that absolutely makes that guarantee, but it has longer run times for, like, it does scale to 14 dimensions, which is awesome, but it'll take an hour hours to certify potentially in 14 dimensions some of these.
Okay. That makes sense.
Right? Yeah. So, and you also mentioned in an earlier chat about, growing balls, for instance, right? So if I were to just take my nearest neighbor collision queries and just try to grow the ball that fits inside the minimum distance to all the points, that can be too conservative. These are growing big convex regions by finding ellipsoids that are, they're polytopes that are pushed out by an inner ellipsoid. So they tend to be very big spaces. And like the shelf example, for instance, it just took 8 regions to get all the places we wanted to get on that. So I don't think it's gotten particularly easier. I mean, we do have some slightly stronger tools maybe, but I think it's worth the computation. You get a lot from a little bit of extra pre-computation. Yes.
Thank you for the great talk. So I was thinking how we would get an approximation factor for the cases when the formulation is not tight. Could we exploit the structure of the problem or use primal dual approaches? Since the shortest path has a corresponding dual problem, we might also have a dual problem for this particular case with convex sets. So do you think developing such approximation algorithms is possible?
It's a great question. So